And let's get started again. All right, so in the first half of this chapter, what we studied were fluids at rest. Now we're going to study fluids in motion. The two important things you studied with fluids at rest were how the pressure increased with depth and Pascal's principle. That is, for an enclosed fluid, if you increase the pressure at any location by a certain amount, the pressure increased everywhere by the same amount. So those were the two important things you learned. Okay, now we'll study fluids in motion. So let's read these bullet points because they're important. The motion in a real fluid is very complicated and not fully understood. We'll discuss the flow of an ideal fluid, and we'll define ideal fluid in a second. Fluids in motion transition from steady laminar flow to turbulent flow about critical speed called Reynolds, characterized by the Reynolds number. So for instance, here is smoke from a cigarette rising. Okay. And here's why smoke from a cigarette rises. So there's a cigarette, and the smoke is hot. It's hotter than the surrounding air. A hot air is less dense and less dense than the surrounding air. So just like ice is less dense than water and it feels a buoyant force, so this smoke feels a buoyant force and it accelerates upward. And it's moving faster and faster. And at this point, it's reached the critical speed where it goes from laminar flow to turbulent flow. So that's what's happening. And what does laminar flow mean? Laminar flow means if you have two atoms that are next to each other, or smoke particles that are next to each other, as long as the flow is laminar, they'll stay next to each other. But once you get to turbulent flow, now you don't know where they are. So they'll go apart very fast, and then their motion won't be correlated. So this is turbulent flow. Okay, and this happens about critical speed for liquids, and it depends on the liquid and so on. Okay, and that critical speed is characterized by a Reynolds number. Okay. So now here's an interesting quote. Heisenberg was a contemporary of Einstein and just smart. So Heisenberg once said, given the opportunity, when I meet God, I'm going to ask him two questions: why relativity and why turbulence? And he says, I really believe he'll have an answer for the first. So that's his opinion about turbulence. So turbulence is characterized by chaotic changes in pressure and fluid velocity. So what this means is, so if you were standing here and measuring the velocity of the smoke, that would be pretty steady. But now if you measure the velocity of smoke in the turbulent area, that would change chaotically. Okay, so it won't be steady at all. And the pressure there would be chaotic. If you put a pressure gauge there, it would be chaotic. The pressure gauge there would read a steady value. Okay. So turbulence is a very tough subject, and we'll talk about it briefly, but we won't deal with it. So here is laminar flow. So what this is sort of showing you is, if this molecule was going there and these two guys were neighbors, they'll be neighbors later as well. Okay. Whereas on the other hand, if you have turbulent flow, here's this molecule going like that, and everything is going crazy. Okay. Again, if you measure the pressure at this location and the velocity at the location, it'll be steady. You measure the pressure and velocity of the fluid at that location, it'll be chaotically changing. Okay. Now, the reason we are interested in this is, so let's say this was oil flowing down a pipeline. And to make a fluid flow, you have to have a pressure difference. Okay. So to make this fluid flow, you have to have a pressure difference between the ends. And if the flow is laminar, the pressure difference for a given flow rate has to be much lower than if it's turbulent flow. So to pump the same amount of oil in a turbulent flow, the pressure difference would have to be a lot more. That means it's costing you a lot more energy. So it takes a lot more energy to pump fluid when turbulence is present. Okay. So, so for instance, so here's another practical application. So let's say this is one of your arteries. Stenotic artery is something that has been constrained, that has been constricted. So this could be plaque deposited in your arteries, and so when the arteries get narrower, the blood has to flow faster. And if this speed is critical, if this speed is fast enough where the flow becomes turbulent, so the flow has become turbulent. And so what this shows you is the flow rate versus the pressure difference you have to maintain between the ends of the arteries. Okay. And you see, for the same pressure difference, for laminar flow, the flow rate would be much higher. But for the same pressure difference under turbulence, less blood is flowing. Okay. So if you want to keep the blood flowing at that rate, you would have to apply a much higher pressure. Okay. So to maintain blood flow rate at that rate under turbulent conditions, you'd have to apply a higher pressure. Your heart would have to work harder. Okay. So plaque deposit in your arteries is not good. Okay. All right, like I said, we won't be talking about turbulence much other than the fact that it's not good for you. Okay. So this is laminar flow, this is turbulent flow. Again, the driving pressure. So for a given driving pressure under laminar flow, you get a much higher flow rate than under turbulent flow. Okay. Viscosity is friction. So because of greater friction, if you wanted to pump honey through a pipe, it takes more energy to pump honey for a given volume, for a given flow rate. It takes much more energy to pump honey than water. Okay. So viscous forces cause resistance when to adjacent layer of fluid move relative to each other. Okay, so viscosity is the friction force between Okay, can you hear me now? Okay, did we get kicked out of the other meeting room? So we got kicked out. All right, so what I'm going to do is I'll come back to my Mac. We'll finish off the lecture with the Mac, okay? All right, let's share. Okay. Yeah, but I'm still in class. Hello. So at what point did we get kicked out of the meeting? Can you tell me what slide were we at when we, slide 25, okay. All right, so thank you. All right, so let me see if we're recording.